Hello, everyone. We're going to start our second lecture today. First of all, any questions about whatever we had covered so far and about the course material and other stuff? No question? Okay, good. Yeah, so your tutorial sessions will start this week. And as you know, this week is not accessible, so you just need to go to tutorial and make sure that you follow the problems and you understand what's going on. But for next week, where we submit after this lecture, we will publish it on the Blackboard. You need to submit your weekly assignments via a link that we will provide under the assessment folder and before the lecture starts next week. Okay, so the deadline is 11 o'clock next Wednesday. As I said previously, we'll take it very easy in terms of marking. The main purpose is to make sure that you spend time and go through the problems before you go to tutorials. Okay? Group working is very welcome, but copying is forbidden. And if you copy, you know that this is not in my hand. If you copy, that would be from university, that would be plagiarism, and that would be fines for that. But you're more than welcome to work in groups and then write your own solution separately. Okay? That's it. Today we are going to continue with game theory and cover the rest of this simultaneous game analysis plus the analysis of sequential games. Let me first describe a little bit what we've done last week. We started with the basic notations of games. How do we describe a game? How do we draw a game? We discussed two major ways that one can represent a game. One is in the extensive form. The other one is in the normal form or strategic form. The extensive form would result to a game tree, and game tree we explained each part of a game tree, the nodes, the decision nodes, the basically information sets, and many other things, as well as payoffs, which were going to be displayed in vectors, and each element of vector represent what each player would get. For instance, first element is what player 1 gets, and so on and so forth. Then we describe how we represent the game in the normal form. Normal form is a matrix form. It's going to be like a couple of boxes, vertical and horizontal, usually very useful for 2 players. But in future, I'll show you how to represent a game with normal form for 3 players as well. But when it's 2 players, that's easily, you can easily define one player, a row player, and the other one is a column player. And again, payoffs will be described in vectors. First element, player 1, second element, player 2. The only tricky part for the last lecture was how to represent a strategy profile of a player when a game is sequential. When a game is sequential, you need to define the actions of each information set. So a simple game that we had, when it was like this, first player moves first and the second player moves second, each strategy profile of player 2 consists of 2 actions. So if you want to write a full strategy profile, it has to be B, 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 N, N, B, or N, N. It is important because the way we represent equilibrium is via representing with a strategy profile. So later on, we started describing the first equilibrium concept, that is dominant strategy equilibrium. And the dominant strategy equilibrium was basically where each player had the dominant strategy. Therefore, for instance, we said dominant strategy equilibrium of, for instance, this game is, where did I say that? Sorry, I missed it. Yep, here we go. So, for instance, dominant strategy equilibrium of this game is C. What was the dominant strategy equilibrium of? Oh, this one didn't have any. For game For example 3, it was CC. This is example 3. Okay? So when we say CC, it is a strategy profile of the player. And when a player has more than one information set, when you want to describe an equilibrium, it must have 2 elements, even though one of the information sets is irrelevant. That's what we're going to discuss today in more details, because most of the equilibrium concepts we discussed last week was for simultaneous games. This only matters for sequential games. Now, later on, we described how to find iterated dominance equilibrium, again based on the dominancy, but now in dominated way. Those actions that are dominated, we simply eliminate them and go forward until we find only one strategy profile that is remained. Then finally, we got to Nash equilibrium. I just discussed the concept behind it, but we didn't go any further. Okay, any questions for the materials last week? Nothing? Great. So before I start, let me say this is not going to be this kind of as boring as it is right now. I usually give several examples. This topic is one of the most applied topics you will find in economics. Okay, there will be plenty of examples, very nice applied examples. But first couple of weeks, I cannot do anything because I need to describe the basics before I can go forward. So these are the basics. They are a little bit boring, but once we know the basics, we go further and give you lots of applications that are more interesting. So Nash equilibrium, the concept is based on mutually best responses. We simply say this is the definition, and what this definition says, it says if S star is mutually best response of all players, that would be called as Nash equilibrium. So when we say mutually best response, meaning that S star is for all small s's as well. So they have to be all the stars. And how can you find a star? A star is there as long as the payoff of that star, keeping all other actions constant, all other players' actions constant, is at least as greater than another strategy profile. Okay? This notation, as I say, may seem a little bit confusing, but when we go through the examples, you will see it is not a difficult notation. Let's see. Let's start with the first example, and that is the coordination game. Suppose there are 2 cars approaching each other on a blind curve. Each can drive either to the left or right. So if they both drive to the left, then they will pass by each other, because left of this car is the right of the other one. But if one goes left, the other goes right, then there will be an accident. Here we represent payoffs with 0, but it could be negative as well. It could be 1, 1, -1, -1, and -1, -1, and 1, 1. What is clear here is that the game is symmetric. Both players have similar payoffs, and therefore we can simply switch the somehow argument. If we get to an argument for one player, that will be the same for the other player. Now let's see how one can find a Nash equilibrium in a game with a strategic form or a normal form. What I will do, I will start with first defining some signs for the best response of each player. Let's suppose best response of player 1 is defined by star. What an ugly star. Let me try a more beautiful one. And best response of player 2 is defined by a dagger. Or delta is easy. Okay? Now, let's find the best responses. To find the best responses of player 1, what we need to do, we need to fix an action or a strategy, here action and strategy are the same, of player 2 and see what would be the best response of player 1. So this is the procedure. I highly suggest you to follow this procedure whenever you want to find Nash equilibrium. You will never going to miss any. Okay? I start with player 1. To find the best responses of player 1, I fix one action of player 2. For instance, I start with L. I fix L. Now, what would be the best response of player 1? So the story is like that. Suppose player 2 plays L. What would be the best response of player 1? L, exactly, because 1 is larger than 0. Okay? The only thing that make you confused here is which element of the vector you compare with each other. Okay, so be very careful what player is going to be compared here. What player's best response are being checked. So player 2 plays L. The best response of player 1 is L because 1 is greater than 0. Now if this is the case, then what we're going to do, we're going to put in a star next to this box. Okay? The reason we do that is because there might be many best responses. We don't want to miss them. And when we switch the player, then there will be other best responses for the other players. Then it would be very confusing if we don't do that. So we put in a star. That simply says that L is one of the best responses of player 1. Okay? Now, the other way of finding the best responses of player 1 is by fixing another strategy or action of player 2. That is R. Now, if player 2 plays R, what would be the best response of player 1? R again, because now 0 is smaller than 1. So I'm going to put another star next to this box. Okay? Now, do we have any further best responses, possible best responses for player 1? Nothing more, because there were 2 strategies by player 2, and we fixed both of them, and we found 2 best responses. What I'm going to do, I'm going to erase a little bit here, because I don't want to make this very crowded. The only thing I'm going to keep is the best responses. 1 here and 1 there. Now, we switch to the other player. What we're going to do now is fixing an action or strategy of player 1 and see what would be the best response of player 2. I start with L again, fix L. What would be the best response of player 2? L. Now comparing the second element of the vector. 1 is larger than 0. This is the only tricky part. So I'm going to put a delta on top of this box. Now fixing action R. What would be the best response of player 2? Is R again, because now 1 is larger than 0. Sorry, for the last one, yeah, here has to be 1 is larger than 0. See, I was very close to make a mistake and comparing this one with the above 0, while I have to do this because this action was fixed. Now, when the game becomes more complicated, more actions, more strategies, and more player, these are the possibilities of making a mistake. So be very gentle, be very careful, and try to follow the procedure to make sure that nothing is missed. So, therefore, when you fix R by player 1, the best response of player 2 is also R. There will be another delta here. So again, I'm going to erase the other things which makes things complicated and then leave the 2 deltas. Now, whichever box that has both delta and a star is a mutually best response. Okay? So in this particular example, we won't have any boxes that have only delta or a star. But there will be future examples that I'm showing you that only one best response, and that cannot be a Nash equilibrium. So here, we have 2 Nash equilibrium. One is LL, and the other one is RR. Okay? So, any set of strategies that is mutually best response, meaning that because here are 2 players here, meaning that it's both star and delta, that would constitute a Nash equilibrium. Any questions? Okay, great. There will be many examples today. We're going to work this out more. So the best thing is just to help me try to somehow get involved, find the best responses, and if you had any questions, just let me know. Now recall the example from the example number 6, where we didn't have any DSE or IDE, and we left it because we couldn't go any further. And let's see if we can find any Nash equilibrium in this game. Again, I'm going to show best responses of player 1 with star and player 2 with delta. Here we have 3 actions, so the sequence is a little bit longer. And since we have equal payoffs, we may sometimes get more than one best response. I'll teach you how to do that. So let's start with player 1 again. I fix action L. What is the best response of player 1? T, because 5 is larger than 4 and 3. So I'll put a star here. Now fix C. What is the best response of player 1? M. And fix R. What is the best response of player 1? B, because 5 is larger than 4 and 3. So we got 3 stars. Remember that you'll get at least 3 stars, because for any fixed action of player 2, there will be a best response. Now in the case that you have equal payoffs and they are the highest, there will be more than one best response. I guess if we switch the player, that's going to be the case we'll see. So now we switch to player 2, fixing T. What is the best response of player 2? R, because 5 is larger than 4 and 3. So I'm going to put a delta here. Fix M. The best response of player 2 is C, because 5 is larger than 0 and 0. And fixing B, the best response of player 2 is, again, L, because 5 is larger than the other. So as you can see, here we have many best responses. In fact, at least 3 for each player. But there's only one box that has mutually best response, and that box is MC, star and delta. So if you follow this procedure, it is very unlikely that you miss a Nash equilibrium. The common mistake and problem that we have, usually in the midterm exam, because this is what you're going to be tested mainly in the midterm exam, is that there are multiple Nash equilibria and you miss some of them because you don't follow the entire procedure. What you found is correct. It's a Nash equilibrium, but it's not all of the Nash equilibria. So you simply look at the choices, it's a multiple choice, and choose the one that is not the proper answer because it is only one Nash equilibrium or 2, and then you'll lose a mark. So not for this example, but there will be some examples that you have more than one Nash equilibrium. I think we'll get, like the previous one, obviously. So be very careful that you make sure that you write all the best responses. Do not trust your mind. Write the stars and deltas on the piece of paper, because if you trust your mind, then easily you will miss them, especially if there's more than one. Any question? No? Okay. So as you can see, Nash equilibrium, as his name looks like, it's very easy to find. At least in this setup, it's very easy to find. Now, let's go a little bit further and see what can we say if there are no Nash equilibria, and see if it is possible that there is an example that there is no Nash equilibrium. Obviously, on paper, it is possible, because there might be a case that we don't have mutually best responses. So just for instance, look at this example and suppose instead of 5, we had 2 for this M. Then the best response for player 1 would no longer become, for player 2 would no longer become C when player 1's action is fixed, because then am I right? No, I'm not right. Let's change 5 to -1, for instance, for player 2. If you change 5 to -1, then when fixing M, C is no longer the best response of player 2, the best response of player 2 will be this and that. We will have two best responses because 0 is equal to 0. As I said, the highest, if they're equal, there will be more than one best response. But the thing is, then we didn't have any mutually best response. Or in other words, we wouldn't have any box which has 2 stars and delta at the same time. So therefore, we won't have any Nash equilibrium. Now the question is, can we say anything further? Or is it all we could say? This game is trying to answer that question. So this is a very similar situation. Suppose player 1 is a government agency and player 2 is trying to gain a payoff G by cheating. So suppose it's a tax situation and the government agency is trying to inspect a firm and make sure that they have done their books correctly and they're paying their correct tax. The inspection may inspect or not. So player 1 can either inspect or not, and player 2 can either cheat or be honest. If player 2 cheats and the agency inspects, the agency would get B, which is basically the benefit, the net benefit of the tax, and the firm would get minus F, which is the fine they need to pay. So B could include F as well. So B is larger than F. I mean, it doesn't matter here, but usually if you're caught, you're not only supposed to pay your taxes, but also you need to pay a fine on top of it. What matters the most here is that firms' 2 payoff will be negative if they get caught. But if they are honest, their payoff is 0. Because they already paid their taxes and there's a cost of minus K for the agency. Obviously, if it is costly, otherwise ATO would inspect all of us every year. The fact that they don't is because it is costly for them. So that's the minus K which is there. Now, if the agency decides not to inspect, their payoff is 0 no matter what. And in the case of cheating, player 2 gets G, which is an extra benefit of cheating in the tax system. Okay? But if it is not, there is no inspection and agent is honest, 0-0. That is our hope. That is the hope that none of the firms are cheaters and they're all honest. So this is a representative of the payoff. Now let's see if this game has a Nash equilibrium or not. We will follow star and delta. The reason I didn't do dagger is I usually use dagger for the third player, so I don't want to even confuse you by the sign. It doesn't matter. No matter, you can use dot and double dot. The only thing that it matters is that you distinguish between the best responses. Okay? So now fix player 2's action C. The best response of player 1 is to inspect, because B is greater than 0. So we will put it as star here. Now fix action H of player 2. The best response of the player 1 is to not inspect, because 0 is larger than minus K. So another star here. Switch the players. Fix I of player 1. Now the best response of player 2 is to being honest, because 0 is larger than minus F. Fix action N of player 1, then the best response of player 2 is to cheat. Therefore, as you can see, I forgot one of the stars, yeah? When we have this, there would be the star here. But as you can see, none of the deltas and stars coincide in a strategy. Therefore, we don't have a Nash equilibrium. The question is, what can we say? Is there anything further we can say? There's a solution to this answer, and is given by, Nash, obviously, which we call it Nash equilibrium in mixed strategies. Okay, so some people prefer to not do mixed strategies right now immediately after the simultaneous game. They'll do sequential and then they do mixed strategies later. But I find it right now the best way, because now we're simultaneous games, and we'll finish the simultaneous game, and then we'll go to sequential games. The only example of sequential games we have so far is the one when example 2, where the second mover, the buyer, moved after then the seller, the producer, and we haven't said anything about the equilibrium of that game yet. So whatever equilibrium we discussed so far was for simultaneous games. Okay? Now for this particular game, the solution is Nash equilibrium in mixed strategies. But what is mixed strategy? Note that whatever we said up to now about players' actions and strategies were basically certain. We said player 1 plays I. Okay? This means that player 1 with probability 1 plays I. And in that case, we will see what would be the response of the other player. But another way of basically representing people's strategy is by mixing them with probabilities. So, for instance, we can say player 1 plays I with probability P, and plays N with probability 1 minus P. Why 1 minus P? Because there are only 2 actions. So the sum of probabilities has to be 1. Otherwise, one would ask us, what would be the remaining? What would happen in the remaining case? For instance, for this tax agency situation, in real-world example, is better represented if we say there is a chance that the ATO inspects agent X. So on average, ATO inspects 20% of agents. I think the real number is much less than that, but let's suppose 20% is the average. So therefore, agent or player 2, agent X, knows that with the 20% chance player 1 plays I, and with 80% chance player 1 plays N. Okay? Now the question is, how do we find these probabilities right now? Because when we go to mixed strategies, then you can sit here if you want. There are many spaces here empty. So the equilibrium here looks a little bit different, because now we no longer say something like MC, because MC means that for certain, with probability 1, player 1 plays M, and player 2 plays C. Okay? This is certain. But when we mix between strategies, then it is possible that players play all their strategies. Therefore, we need to represent a probability for each of them. For instance, one mixed strategy here is half, quarter, quarter. What does that mean? It means that player 1 plays T with half a chance, player 1 plays M with a quarter of a chance, and player 1 plays B with a quarter of a chance. Okay? The sum must be 1. I'll explain this formally very shortly, but what matters the most is that now you cannot say MC is an equilibrium. What you can say as an equilibrium is a sequence of probabilities. Okay? So this is still full information game. This is totally different to an example that I gave you last week, which was whether it's going to rain or not, should we take an umbrella or not. That thing is uncertainty. These probabilities are different than uncertainties. It just simply means that I mix between my strategies. Okay? Those games, which we call them later on games of incomplete information, is the case that we don't know what will happen in future, or there's a state in nature that moves which we are not sure about it. There will be probabilities there for each of the possibilities, but that is a totally different scenario, because that is out of our hand. Here, the probabilities are in the hand of player 1. Therefore, they are chosen endogenously. Now, after this brief explanation, here's the definition we use. A mixed strategy for player I, sigma I, assigns to each pure strategy Si a probability. Okay? So the half, quarter, quarter that I just showed you is a sigma. So sigma is a vector of probabilities that assigns a probability to each of the strategies of the player. In that example, there were 3 strategies, therefore sigma had 3 elements. Now, there are two things that we need to be careful. Before that, note that sigma is between 0 and 1, each element of sigma, because it is probability. It cannot be greater than 1. And the sum of the sigmas for every s in capital S is equal to 1. That's why here we had sum of half plus quarter and quarter equal to 1. Now, there are 2 points here. A pure strategy can be viewed as a special case of mixed strategy. What would be that? Those probabilities? Obviously, when I say player 1 plays I, it means that player 1 plays I with probability 1 and plays N with probability 0. So a pure strategy is obviously a special case of mixed strategies, but we usually don't represent them in probabilities because 0 simply means that this is not going to happen, and therefore we simply eliminate it. But this point, the first point simply says that it's a special case, so therefore mixed strategy representation of a game is a much more general way of representing a game. And the other thing is, when using mixed strategies, the objective of a player is to maximize the player's expected payoff. Okay? So here, we no longer have the exact payoff. So, for instance, in the MC, we would simply say, because 5 is larger than 0 and 0, therefore, I'll play 5. So I want to maximize my payoff. Because when I play 5 with one probability, with probability equal to 1, 0, 0 never going to happen. But now, since there is a probability for each of these strategies, my expected payoff for this set of probabilities, if player 2 plays C, is half times 0, 1 plus 1/4 times 5, plus 1/4 times 0. That's what we call expected payoff rather than payoff. So expected payoff simply means probabilities times payoff, sum of them. Okay? So, now look at example 8. Consider a mixed strategy where player government plays inspect with 1/3 probability in third of times, and with 2/3 does not inspect. So that would be one example. And then player 2, for instance, cheats in 1/4 of cases and is honest in 3/4 of the cases. This is a possible mixed strategy. Obviously, this is not a mixed strategy in Nash equilibrium. I haven't even said how to define a mixed strategy at Nash equilibrium. It is too early. The next slide is that. But we are just defining possible mixed strategies. Then I'll let you know how to find the Nash equilibrium in mixed strategies. Definition 7 is where we find Nash equilibrium in mixed strategies. A mixed strategy profile sigma star constitutes a Nash equilibrium if, for each player I, the payoff of that particular mixed strategy fixing other mixed strategies or mixed strategies of other players is at least as large as any other combination of probabilities. Okay? Again, this is a very general representation, but in problems there are easier ways to find them. So, in other words, each player's mixed strategy is best response to the mixed strategy choices of other players. Okay? So we used to say each player's strategy is the best response, choice of other players' strategies. But now here we say each player's mixed strategy, rather than just saying one, a mix of them. But the question is what mix? The what mix is given by this, and there's a way of finding it in problems. Before I go any further, to somehow discuss a little bit about what happened here. This is, as a result of this, there was a proposition by Nash, which resulted in his Nobel Prize. Obviously, as you know, the Nobel Prize Committee would not specifically say why did we give you the Nobel Prize. They say in general for your contribution in game theory to economics. That's something like that. But the finding of Nash, which was very interesting in his thesis in 1950, was that he came with a theorem saying that every game with finite set of actions and strategies has at least one Nash equilibrium in mixed strategies. Okay? And obviously there are conditions that will be at least and at most only one mixed strategy equilibrium. So again, he didn't call it Nash equilibrium at that time. He called it mixed strategy equilibrium. But then later on, we changed the name to Nash equilibrium in mixed strategies. So why is it an interesting finding? It simply says that as long as you have finite set of actions and strategies, which is the case in almost all situations in economics, then you will be able to find an equilibrium in mixed strategies. Okay? So because what confuses us up to now in many of these lectures is that what if we couldn't find, for instance, IDE? What if we couldn't find DSE? So now, by the proposition of Nash, you know that there will always be a Nash equilibrium in mixed strategies. So if I gave you a question in the exam and said, find the Nash equilibrium in mixed strategies, and one of the choices says there exists no, just eliminate that choice, because otherwise Nash wouldn't win a Nobel Prize. So there will be one. The question is how to find it. Okay? Now, in the next slide, I'll show you how to find it. There are two things that you need to remind before using the technique to find the Nash equilibrium in mixed strategies. Define SI plus, which is the strategy of player 1 with positive probability. Okay, so in pure strategy equilibrium, we simply have one strategy with positive and all others are 0. But here we have a much general definition saying that SI plus is the set of strategies of a player that gives a positive probability to them. And most of the cases, we have SI including all the strategies. For instance, here when I say a quarter, quarter, half, half, quarter, quarter, this means that S plus I is the same as SI. Is it? Did you get what I mean? SI is TMB. Okay? Now, S plus I is the set of strategies that is played with positive probability. Now, all of these probabilities are positive. Therefore, SI plus is the same as SI in this particular example. Now, what I wanted to say is that this is not a rocket science. This is just a very simple notation of those to eliminate a situation where you get 0 to many strategies. If S plus is that, each player is indifferent among all pure strategies he plays with positive probability. Okay? What does that mean? It means that the intuition is like that. Suppose I'm going to play a penalty shootout in football with a goalkeeper, and I'm going to mix between obviously left and right, because if I say I always kick to the left, then he's going to jump to the right and get the ball. Now, I'm going to give some probabilities to the left and some probability to the right. Suppose that my skills are such that I have a better chance if I go to the left, because I'm right-footed and putting the ball to the left is easier for me. Now, if I give equal probabilities to these two, then there's a higher chance for me that I score to the left. Then I always play left. Then the goalkeeper obviously knows that. So if I mix equally between left and right, then he'll always jump to the right and get the ball. So what I need to do, I need to give equal expectation for the goalkeeper for both right and left. And how can I do that? By mixing the probability times the payoff that I get, or my skills. So therefore, the left-hand side, which is my better side, would be kicked by lower chance. So you may find this odd, but you have to do this. Otherwise, if the thing is, in reality, most players don't know what are the best sides of the other player. But if they knew, then you need to shoot to the other side more frequently, because that will be that would be the best strategy, because if there's epsilon more chance for the player, for the goalkeeper to get the ball from one side to the other, then he would always jump to the side with a higher chance. So what we mean here is something exactly the same, but in terms of notation. We mean that if you want to mix, it has to be the case that it is the expectation of other player by your action will remain the same. Otherwise, the other player would always have a better chance to do. Better strategy to do, not better chance, better strategy to do. The pure strategies are at least as good as any pure strategies he plays with zero probability. So this is not much relevant for our purpose, because in most of our cases, we don't have actions with zero probabilities. But if we have, for instance, suppose we have a dominated strategy, then that should be played with zero probability. Then in that case, the mixing, the payoff of the positive probability thing, which is S capital plus, has to be greater than the payoff of those which we give zero. It is intuitive, because it simply says that if you give zero probability to one of your actions, suppose we have a third action for the goalkeeper example, and that is for me to shoot to the sky. Okay? So I'll give zero probability to that action because it will give me nothing. So if that's the case, then the payoff of other actions, which is either left or right, has to be greater than payoff of shooting to the sky. Okay? So it is, as I said, a bit intuitive. So you won't give zero probability to a strategy unless it is at least weakly dominated by other strategies. So having said these two, we are ready to find a mixed strategy in Nash equilibrium. Now you may say, how? But you will see how very easily. Suppose in that example 8, B is equal to 1, F is 2, K is 1, G is 3. I'm going to draw the example again here. So we have player 1 and 2, I, N, C, H. Player 1, 2, C, H, I, N. Now we had inspection, cheating, B was 1. Oh, sorry, B had to be greater. But anyway, let's just suppose B is 1 for the moment. 1 and minus 2, then minus 1 and 0, then 0, 0, and here we have 3 and 0. Am I right? Everything good? Let me make sure that everything is fine before we proceed. See, I made a mistake. Here has to be 0, 3. And none of you told me. Why? This is the bad thing about this. When you change the slide, you cannot undo anymore. So 0, 3. Now, this is the game we're dealing with. We want to find the mixing strategy in Nash equilibrium. We had 2 points to say. One was that if you want to mix in an equilibrium, it has to be such that the other players is indifferent between his strategies. Otherwise, he would always choose one which gives higher payoff. So, first of all, I would define an ambiguous mixed strategy with variables, and then using that argument, I'll try to find the variables. What do I mean by ambiguous? I mean, there are 2 actions for each player. So mixing for them is simply probability P time, and the other one would be 1 minus P, because the sum has to be equal to 1. So suppose player 1 plays action I with probability P, and action N with probability 1 minus P. Okay? So I could use any other variable than P. So for instance, C, delta, whatever. So that would be the probability for action I, and 1 minus that would be action N, because there are only 2 actions. For player 2, we use Q usually. Now I can say player 2 plays C with probability Q, and H with probability 1 minus Q. Okay? So these are my unknown. And if I can find P and Q, then I can find a mixed strategy Nash equilibrium. And that is basically the probabilities that players give to each of their strategies. Now, how do I find P and Q? The only way I can find it, and the easiest way, is through the argument that I told you. So the expectation of other actions are strategies of one player based on the other player's mixed strategy has to be equal. What does that mean? It means that if player 1 plays I, it has to get similar expectation from for playing N as well. So we need to find the expected payoff of player 1 for playing I, and player 1 expected payoff for N, and then put them equal to each other to find Q. So if player 1 plays I, she knows that with probability Q, she gets this, which is 1. And with probability 1 minus Q, she gets this, which is minus 1. Okay? So, as we just said, to find the payoff of player 1, we need to find expected payoff. That is the sum of probabilities times payoffs. So, the first thing would be this multiplied by that, and this multiplied by that. So, the expected payoff of player 1 for action I is Q times 1 plus 1 minus Q times minus 1. Okay? And that is what I wrote here after some simplification. We got 2Q minus 1. Okay? So this is what we got for the expected payoff of player 1 for playing action 2. So this is back to my example. I think I said my payoff of playing left and right, but I was wrong. I should say the goalkeeper's payoff of playing left and right. So in that particular example, it's very hard to justify because the payoff is either 0 of not getting scored, or 1, or minus something if the ball is goal. But just imagine that the payoffs are different. Now if I want to mix, I should mix such that goalkeeper has similar payoff, expected payoff by jumping left or right. So, and that's how we do it. We simply multiply the probability of that strategy to the payoff of player 1. Now let's do it for the other strategy, expected payoff of strategy N. Now it's Q times 0, 1 minus Q times 0. So here again we need to be very careful, especially when there are more than 2 strategies and there are 3 of them. Be very careful to multiply things correctly. If you multiply Q to the second element, then you'll get a completely different outcome, which is wrong. So those are the common mistakes that I observe the students make. Usually, if you follow the instructions that I'm telling you, it is very unlikely that you make such kind of mistakes. So Q times 0 plus 1 minus Q times 0, which is obviously 0. Now, if we put these two equal to each other, that is, expected payoff of I is equal to expected payoff of N, then we'll get 2Q minus 1 equal to 0, and that gives us Q equal to half. What does this mean? It means that in a Nash equilibrium in mixed strategies, player 2 must give equal probabilities to each of her actions. Otherwise, player 1 would have always a better outcome, and therefore that cannot be a mixed strategy equilibrium. Now, what remains is to do exactly the same thing for the other player, so switch the players in order to find P. Usually for symmetric games, this is much easier because for symmetric games you don't have to do it twice. Once you find Q, that will be P for the other player. But here it is not a symmetric game, therefore we have to do it twice. So now fix any action of player 2, for instance C. The expected payoff of player 2 plays C is P times 2 plus 1 minus P times 3. Okay? Yeah. P times minus 2, sorry. P times minus 2 plus 1 minus P times 3. And that's what you get, which is 3 minus 5P. The expected payoff of player 1 from playing N, sorry, the expected payoff of player 2 from playing N, so this is wrong, I need to rephrase that. So this has to be expected payoff of player 2 from playing H. I should remember to fix that in future, but anyway. So player 2 playing H, it is P times now 0 plus 1 minus P times 0, which is obviously equal to 0. So this is right. Don't worry about it. The only thing which is not right is this and this. This has to be for player 2, and the action has to be H. So again, we have 0. So one thing is clear is the clear thing is that both of the players have a 0 expectation from their second action. Okay. So now 3 minus 5 equal to 0 gives us P equal to 3 over 5. Now the way we represent a Nash equilibrium in mixed strategy is like that. We just represent the probabilities. So for a 2-player 2-action game, it will be P star, NE in mixed strategies is P star, 1 minus P star, Q star, and 1 minus Q star. Okay? And these are basically the probabilities that each player gives to each of their actions. You will see how complicated this can become if players have more than 2 strategies. So for instance, if each player has 4 strategies, then we need to write 8 probabilities in one Nash equilibrium in mixed strategies. But that's not what I'm going to do in this course. Our purpose is not just to simply make things hard for you. Our purpose is to make sure that you understand the stuff, okay? So therefore, in the worst case scenario in problem sets, we may go with 3 actions. And if there are 3 actions, then you need to do things twice. What does that mean? It means that you need to find the expectation from the first strategy, second and third, and once first and second equal, one second and third equal, and once first and third equal, because now you have more variables, okay? Now, if there are 3, for instance, if you go back to this example, you should write P1, P2, and 1 minus P1 and P2, okay? And you will have enough equations to solve for this, because now, since you have more strategies, then you will have more equalities between them. So 2 of them will be useful for you, and that is expectation, for instance, of T has to be equal to expectation of M, and then expectation of M has to be equal to expectation of B. Of course, by transitivity, you know that would result to expectation of T equal to expectation of M, sorry, expectation of T equal to expectation of B, but 2 is enough for you because you only have 2 variables, P1 and P2. The same is true for the other player, Q1 and Q2, 1 minus Q1, Q2, okay? So you may get one problem like that in your problem set. And as long as you'll be able to somehow come up with a logical argument like this one, even if your final answer is not correct, you'll probably get the full mark. That's problem set, as I said. It's not supposed to be very accurate. Any questions? We have another example which is the case that we both have Nash equilibrium in pure strategies and Nash equilibrium in mixed strategies. What this example is trying to show you is that if there is a Nash equilibrium in pure strategies, it doesn't mean that you cannot find a Nash equilibrium in mixed strategies. So based on Nash's theorem, you will always be able to find a Nash equilibrium in mixed strategies. Okay? So this game is a chicken game. It's a very famous game. Suppose there are two teenagers driving toward each other. They pull out their steering wheels and they're just trying to show their peers that they're heroes and they're not afraid of anything. So they have two possible actions: to drive through each other or chicken out, or basically either put it on a brake or simply move the car to any side. Okay? So if they are chickening out and the other player is not chickening out and goes straight, it will be very humiliating in front of their peers, and therefore they don't want to somehow go either to left or right or stop once the other player is going straight. If both go straight, then obviously there will be a clash and they will both die, or if they don't, they will become disabled. That is the worst outcome for both players. And obviously, if both of them chicken out, there's zero payoff for them. So they're better off not even playing the game. And there won't be as much humiliation as this case, but it is not a good outcome as well. So this is the best. So if one drives, the other one chicken out, that one who drives is going to become the champion and the hero, and the other one becomes humiliated. Now, if you want to find the Nash equilibrium in pure strategies, there are two Nash equilibrium. One is D drive chicken, and the other one is chicken drive. So I leave it to you. Use the star and delta. You will be able to find it easily. There will be only two boxes that have both of them, this one and that one. Now, the question is how to find the Nash equilibrium in mixed strategies. Again, we're going to use the same method. Now here I've got it in the slides. The previous one I worked it out here, but here now I've got it here. And I'm going to use it in a slightly different way, although with exactly the same logic, but I'm going to use a slightly different way. Here, whichever you're more comfortable, you're free to use. The outcome is obviously the same for both. Now, I give P to chicken, 1 minus P to drive, Q to chicken, and 1 minus Q to drive for the other players. So, thankfully, this is a symmetric game. Therefore, if we find for one player a Q or P, we can substitute for the other player. Now, what I say is row player prefers chicken over drive if and only if the expectation of playing chicken is larger than expectation of playing drive. So this player prefers chicken over drive if Q times 0 plus 1 minus Q times 2 times minus 2 is larger than Q times 10 times 1 minus Q times 9 minus 9. Okay? These are the things that I wrote here. So in the previous example, I simply put them equal to each other and found an equation as a function of Q. But here, I'm going to use the logic. I'm going to say, if this is strictly to the left, then you will not mix. So as long as this, when you simplify that, you'll say Q, you get Q less than 7 over 17. So this argument simply says that if Q is less than 7 over 17, then player row always prefer chicken over drive. Okay? Now, if the opposite happens, that is, Q is greater than 17, then player 1 always prefer drive over chicken, because now if Q is greater than 17, then this inequality will be to the other side. Now, the only way for player 1 to make sure that player 2 does not have a strictly better strategy is to choose Q equal to 7 over 17. Okay? This is exactly the same argument, but in a different way of writing. Of course, for solving problems, writing in the previous example way is much easier. But if you like to write it this way, and explain your answer, how to find 7 over 17, you're welcome to do that. Mostly you will be examined here in an exam by multiple choice, so you're free to choose any of these methods. As long as you just find the right number, you'll get the mark. So now the good thing is once we found 7 over 17, we found the Nash equilibrium in mixed strategies because the other player is symmetric. So the Nash equilibrium in mixed strategies here will be 7 over 17 and 10 over 17, 7 over 17 and 10 over 17. Okay? That's how you write the Nash equilibrium in mixed strategies. And this graph is also trying to show you exactly the same thing that I just said, saying that if the probabilities P and Q are anything except that 7 over 17, then the other player has a best response to basically not mix or do something always. So the other player would always have a better response. Therefore, the only point that gives us the mixed strategy equilibrium, which is basically both players mixing with probabilities, is 0.7 over 17. Okay? Any questions? Nothing? Great. So that's all we say for the Nash equilibrium in mixed strategies. If you don't have any questions, then I'll move forward to games with sequential actions. No question? Great. Now, before I go any further, I want to remind you a table that I showed you in the first class, which is this one. So, as I told you, in terms of timing and information, you can change things a lot. But here, so far, we were in a game of a static with complete information, and we didn't say anything about dynamic games, except that one example which we wanted to show you how to write the information sets. I had to do that because otherwise you will always think that the information sets are one and there will be a dash line between the two decision nodes. So I had to give you an example last week. Otherwise, all the equilibrium concepts so far we learned are for complete game of static. So this. And obviously, what we learned today is a further concept of complete information game and static, and that is mixed strategy NE. So mixed strategy NE goes under the category of NE. So it's nothing more than that. Although it's a different way to find it, but it is the same concept as Nash equilibrium, and that is the best response. Now, what we're going to do later, we're going to switch to this part of the course. And we're going to study games of complete information with dynamic moves, or let's say sequential moves. Dynamic here we usually mean sequential, okay? That's some kind of similar words that we use. The equilibrium concept here is called subgame perfect equilibrium, and that's what I'm going to teach you next. So let me get back to the slide that we were having. But before we can proceed to subgame perfect equilibrium and what it is, we need to know a little bit further stuff. So far, except example 2, all the games are simultaneous. But now, example 10 is another game that can happen sequential. Suppose a firm, which is an entrant, decides whether to enter a market or not. The incumbent, upon observation and entry, has two options: to accommodate or to fight. Good example that I'm giving you, I'm not sure whether you remember that time or not. There were times before where Costco was not in Australia. We only had Coles and Woolies, and IGA obviously a small share of the market. Suppose Coles and Woolies are same companies, are owned by one company, and they have the market. Now, there's a threat by a large company, large American company called Costco, who who wants to enter the Australian market for grocery, obviously. Now, once the Costco came to Australia, Coles and Woolies has two actions. Either accommodate Costco, let them get some of the share of the market, or fight with them and compete in terms of prices and basically make it hard for them to stay in that market. Therefore, here we have two actions. Obviously, it is not a symmetric game. For player one, which is Costco, is deciding whether to enter or not. For player two, which is Coles and Woolies, is decide to whether accommodate or fight. So if player one enters and they accommodate or cooperate, it's another word, they both get half of the market. So it will be shared. So 2 and 2. But if Coles and Woolies decide to fight, then they get both -1. Because then they cannot cooperate and increase the price. They need to bring down the prices and then still paying the costs. Therefore, they get negative payoffs. If player 2 decides to accommodate and player 1 does not enter, then obviously player 2 gets 4, because it doesn't matter whether you accommodate or fight once Costco doesn't come to Australia. So if Costco decides not to come to Australia, Coles and Woolies get 4 no matter what, and Costco gets 0 because they don't pay any cost and they won't get any profit for that. Now, so what I'm going to do here, I'm going to justify for you why do we even study subgame perfect equilibrium. Because first thing you can ask me is that, what was the problem with Nash equilibrium? And again, games of sequential games, again, you can find Nash equilibrium, obviously. There will be many of them, more than one usually, but your first question will be, what is the problem with that? Why do we need to study anything further? Now, this is the reason. If you draw this game in extensive form, I mean, first let's find the Nash equilibrium. Again, I'll give it to you as an exercise, but you can use a star and delta here. Let's maybe do it here. Okay, fix A, the best response of Costco is to enter. Fix F, the best response is to not enter, because 0 is greater than 1 minus 1. Now fix enter for Costco, the best response of Coles and Woolies is to accommodate, because 2 is larger than minus 1. And fix not enter, the best response of player 2 is to both accommodate and fight, because 4 is equal to 4. As I told you, when they're equal, they're both best responses as long as they're the largest or the only 2. Okay? Now there are two Nash equilibria here, EA and NF. Okay? Now let's see what is the problem with NF. So this is the biggest problem with the concept of Nash equilibrium. Nash equilibrium is a very good thing, but it is a very large set. We need to make this set a smaller. Why? Now look at NF. What does NF mean? NF means that Coles and Woolies will fight, but Costco does not enter. What does that mean even? So when Costco did not enter, who are they fighting with? So if you want to describe this Nash equilibrium, or if you want to somehow describe it as the final outcome of the game, in reality people will laugh at you. So if you tell, for instance, if you're a consultant to the managers of Coles and Woolies, and you told them that the equilibrium is that you fight and they don't enter the market, they just simply laugh at you and say, what the hell do you mean? How come we can fight with somebody who didn't even enter the market? So that's why we need further concepts to somehow eliminate such Nash equilibria from the game, which are, we call it non-credible Nash equilibrium. So the threat of fighting is non-credible, because the other one will never enter. Okay? So that's how. So the question is, how can we rule out such NE? The answer is via the subgame perfect equilibrium. So subgame perfect equilibrium was introduced by Zelton. I remember in the first class I showed you the history of Nash equilibrium. This is, I guess, happened in the 60s when he somehow introduced this method. Now we are in our papers, in research papers which are up to date. Obviously 2019 paper or 18 paper are the most recent achievements, we usually decide to focus on subgame perfect equilibrium if they are different than Nash equilibrium, okay? So if it is possible, we prefer to write in our propositions that this strategy is a SPE, subgame perfect equilibrium, rather than Nash equilibrium. Sometimes the set is the same, sometimes the Nash equilibrium set is larger, but any SPE is always a Nash equilibrium, okay? So this set of SPE is at least as small as, or let's not, this is not a good way, say weakly is smaller than the set of Nash equilibrium. But but the question is, what is an SPE? To find out what is an SPE, we need to have definition 8 and then find SPE. What does definition 8 mean? A subgame of a game in extensive form is a subset of the game having the following properties. Okay? So what I'm going to do, I'm going to define a thing which we call it subgame. The subgame has two properties. It begins with an information set containing only a single decision node. Okay? Those information sets where we're dashed between each other and we had two decision nodes, those cannot be a subgame. And contains all nodes and its successors. So everything below that will be within that subgame. So this is the first thing you need to remind. Now second, if a decision node is in a subgame, then all other decision nodes are in the same information set, has to be in the same subgame. What does that mean? It means that if, for instance, you have a game like this, and you call this decision node, and you, for instance, say this decision node is in a subgame, then the other one, which is connected by the dash, has to be in the same subgame. So we cannot have two different subgames where one decision node is in this one and the other one is in the other one. Okay? So this only happens for a game that has simultaneous actions. Let's first focus on the part A, which is the case for games of sequential actions. What I'm going to bring you is this example and work out with you how many subgames this game has. So remember, the first thing says that an information set that contains only one decision node. Okay? Now, before I proceed, there are some corollaries here that I need to read before I go further. That is basically the whole game is always a subgame. So the whole game is always a subgame because the whole game starts with a single decision node. You cannot have a game starting with two decision nodes. Okay? And it includes all the successors. Therefore, the whole game is always a subgame. Now, if we go back to our example, now can anybody tell me how many subgames this game has? 2? Why 2? 4? Why 4? So first, to find subgames, first find decision nodes. Okay, that's the easiest way. How many decision nodes do we have here? 3. Okay, are there any of those decision nodes that include multiple decision nodes? Like the dashed line between them? Of course not. Therefore, we have 3 decision nodes that are singular. So all decision nodes satisfy the subgame criteria. So we have 3 subgames. 1, 2, and obviously whole game 3. Okay? Now, if you look at the 2 points that I just said, all 3 of these will satisfy those 2 points. So now, how about this game? How many subgames do we have here? Let me ask you the opposite way. Can this be a subgame? No, because this part of the game has another decision node which is somewhere else. Based on point 2, this cannot be a subgame. Now, can this be a subgame? No, because point 1 says a subgame can only be a case where there's one decision node. Multiple decision nodes, so the subgame must start with one decision node. when the game starts with 2 decision nodes like here, this cannot be a subgame. So therefore, this game has only one subgame, and that is the whole game. Okay? For games with only one subgame, the set of Nash equilibrium and set of SPE will be the same. You'll see why in the next couple of slides. But what I'm trying to say here is that our interest is for those games that have multiple subgames. That's what we're planning to look for here. Now, if I get back to my points, oops, I just substituted 2 slides. If I get back to my slide, which was here, so now, oops, which was here. So now we know how to find subgames. First, it begins with an information set that contains only a single decision node. Now, if there are multiple decision nodes, it cannot be the case that one of them is in one subgame and the other one is another subgame. This can conclude that those decision nodes that have a dash in between them cannot start a subgame. You need to go one step back to find the subgame for those games. So therefore, all other games that we study up to now, since they were simultaneous, had only one subgame, except example 2. Now, how about example 10? How many subgames do we have here? How many decision nodes do we have? 2. Is there any of those which have multiple decision nodes? No. Are they include all the successors? Yes. So we have 2 subgames, one here and one there. Now transform this game as follows. Suppose Costco and Coles and Woolies decide at the same time whether to fight or enter or not enter. So they are both, the managers are both into separate rooms, and at the same time, Costco decides whether to enter or not, and Coles and Woolies decide whether to fight or accommodate. Now the way that game changes is as follows. This game would now change to another information set 2. There will be a dash line. There will be here AF and 0404. So if that's the case, then this game only has one subgame. So my aim here is to show you that a tiny change into the representation of the game can change a lot of stuff. So be very careful when you read problems to make sure that you understand the timing, the sequence, the information available, and the payoffs. Okay? So here we have 2 subgames. Now, we need definition 9 to be able to find subgame perfect equilibria. First of all, the only way to find subgame perfect equilibria in this course, obviously not in general, in this course is via the game tree. So whenever you want to find the subgame perfect equilibria, you need to draw the game tree, find the set of subgames, and then do the following that I just said, that I will say. A strategy profile is called subgame perfect equilibrium, or SPE, if it induces a Nash equilibrium in every subgame of the original game. Okay? So now, if you have 3 subgames, if there is a Nash equilibrium in all 3 of them, that would be a subgame perfect equilibrium. So if it is a Nash equilibrium only for 2, that cannot be an SPE. Now, a SPE is found by the use of backward induction. This is a brilliant way that Zelton introduced, and he obviously won a Nobel Prize for that. So we start with the final subgames, we find the Nash equilibrium, eliminate anything else except that Nash equilibrium, and go forward until we finish, and then the sequence we found will be the SPE. Now, if any subgame has multiple Nash equilibria, we repeat this sequence again. Okay? So now let me read it formally. Start with each of the final subgames and identify the NE, the Nash equilibrium in that subgame. NE in a subgame is very easy. So I mean, if there are multiple steps in a game, the worst that can happen is that the NE will become simple NE that we just found in the boxes in the strategic form, the previous examples. But now, once you found the NE of a subgame, replace the subgame with the NE, so eliminate everything else except that NE, and then go one step up. Now, from that point forward, if you want to go down to see the payoffs, the only direction is that NE, nothing else. And do that for the whole game, then you'll find the subgame, perfect equilibrium. Given this process, whether this NE is any subgame, a sub SV is necessarily an NE. Because if it is an NE in each subgame, then it has to be an NE of whole game. But the reverse is not right. So it's not the case that all NE are SVE as well. Okay? As I said, the set of NE is usually larger than the SVE, or at least as large as the set of SVE. Now let's see, how do we find SVE? Again, I show you a very simple methods, but you just need to follow the instructions that I give you. If you follow them, you'll be able to find NE easily. First of all, identify the subgames of the game. As I told you, there are 2 subgames in this game. Okay? Now start backward. From the end of the game, go forward up. The lowest subgame here is 2. Remember that this is the decision node of player 2. To find the NE of this subgame is simply to find the best response, because it's just one player moving, nothing further. So if player 2 has these 2 options, which one would she choose? A, because 2 is larger than -1. So we will put an arrow here instead of, crossing. There's another way, but we put an arrow here and move to the next subgame. But after this point, whenever we get to this smaller subgame, we only know that this is a possible direction. Okay? We don't know this part of the game anymore. It was eliminated because it is not the NE of that subgame. Now the next subgame is the whole game. Now the decision node is for player 1. Player 1 decides whether to enter or not. If player 1 enters, she would end up to this direction. As I said, we don't care about this part anymore. We cross it. Okay, that's the tricky part. So if player 1 ends up here, her payoff is 2. If she ends up there, her payoff is 0. Now, what is the best response? Is obviously enter, because 2 is larger than 0. Now, this game has only one subgame perfect equilibrium, and that is EA. Because we are done. We had only 2 subgames, that's it. We are done. So by this argument, we got rid of the bad Nash equilibrium, which was an F, the non-credible one. And therefore, this is the good Nash equilibrium. Obviously, sometimes we find unreasonable SPEs as well, but this is a smart way of getting rid of some of the NEs that are not reasonable. Okay, any questions? The rest of the lecture will wrap up. We'll continue with some examples. I think 2 or 3 examples with the how to find the SPE. So if you have a question, please interrupt me somehow. Come with me when I say something. When I ask you a question, try to follow and try to answer, because that's the only way. That's the best way to learn this SPE. So what we're going to do here is to kind of find the SPE of the following game, voting by veto. Player 1 moves first, X, Y, Z, and then player 2 decides between the remaining options. If player 1 chooses X, then 2 has only Y and Z. Player 2 has X and Z if player 1 chooses Y, and player 2 has X and Y if player 1 chooses 2.3. Now you may ask me, why did I choose 1.1 here? I did it intentionally. I just wanted to tell you that this doesn't matter much. Because here, as you can see, player 1 only has one decision node. I could simply write 1 rather than 1.1. But these are just notations. It doesn't matter. So what matters is that player 2 has 3 decision nodes, because players move sequentially. Therefore, this has to be distinguished by 2.1, 2.2, 2.3. If you write 2, 2, 2 here, this is wrong, and you lose mark. So you need to be precise here and distinguish between the information sets of the second player. Now, let's first find the subgames of this game and then the SPE of the game. What are the subgames? How many subgames are there here? So try to think something. I mean, you're not going to lose anything. 4. Yeah, exactly. Why 4? We start with the decision nodes. There are 4 decision nodes. They all include all the successes and they're only the decision node. So they're not multiple. Multiple of them with a dash line between them. Therefore, one subgame is here, the other one is there, and this is the one, and this is the last one. Okay? So we have 4 subgames in this game. 3 of them are relevant to player 2, and 1 is the whole game. Now, we start the backward induction and find the NEs. I start with the left subgame, 2.1. In the 2.1, it is player 2's turn to move. Now, what is the best response of player 2? Z, because 2 is larger than 0. So we draw an arrow here. And I remember when I was a graduate student, I passed this course when I was a graduate student in Sydney. I hated when the lecturer did that. I would say, why the arrow is backward? It has to be upward. So if some of you have this situation, don't bother. You can use a star. You can use dot. You can use whatever you want. This is just a method to find a way that we don't miss this. Because we go to the next sub-game, we want to come back to this in future, we want to know where we end up. So, therefore, let's use the method of my lecturer, who ended up becoming my supervisor, and say Z is the best response of player 2. For the next sub-game, 2.2, again, it's player 2's turn. The reason that I'm repeating this every time, because if you if you confuse between players, then you will obviously find wrong best responses. So, again, remind yourself every time you deal with a sub-game that whose turn it is, who's the decision maker. Here's again player 2. What is the best response? Again, Z, because 1 is larger than 0. So, another arrow here. And the third sub-game, 2.3, player 2's turn again. What would be the best response? X, because 2 is greater than 1. Another arrow here. Now, we simply eliminated Y here, X here, and Y there. You don't have to cross them, because this is an extra thing I do in the lecture to make it clear. More clear for you, but you don't have to do it. As long as you draw the arrow or you identify that best response, you're done. Now, let's go to the whole game, or information set 1.1. Now it's player 1's turn to move. Player 1 knows if she plays X, she'll end up here, because this part of the game doesn't exist anymore. When I say doesn't exist, I mean for the moment, for this particular equilibrium analysis. When player 1 plays Y, she would end up here. And when player 1 plays Z, she will end up here. Now, what is the best response of player 1? It is Y, because 2 is larger than 1 and 1. So I'm going to draw another arrow here. So we found a subgame perfect equilibrium. What is the subgame perfect equilibrium here? Okay, so here's now the problem. So most of you usually say YZ, but my question is which Z? If you say YZ, did you represent the full strategy set of the second player? Obviously not, because second player can play Z here as well. So as I told you in the first session last week, when you have more than one decision nodes in a strategy profile, you need to describe all the actions of that strategy profile, even though they're not played. Okay? So the subgame perfect equilibrium here is Y, Z, Z, X. So if this was a multiple choice question, there will be a first choice, which is this SB is YZ. And I'll usually put this at the bottom. I want to make sure that you guys understood. So if you choose YZ, you lose mark. Because YZ is not the equilibrium. Here it's incomplete because it doesn't say which information set of the second player. Second player has 3 information sets. And even though these 2 will not be played in the equilibrium, they must be mentioned in equilibrium. Why? Because the other alternative, which is Y, Z, Y, is not an equilibrium. So if you say only Z, I'm not sure whether you're talking about ZZX or YZXY or YZX. There are many other combinations as well. So as you will see in this week's tutorial, we make games more complicated and ask you to write the whole set of strategy profiles. The purpose is to show you that there are many alternatives, and therefore you cannot simply write YZ because it is incomplete, it is not fully representative of the whole situation. One last thing that I wanted to tell you before we go to the next example is a subgame equilibrium path. I think I missed it here in this lecture, in this slide. The subgame equilibrium path refers to the actions chosen along the SPE. Okay? So what you guys said, YZ is the subgame equilibrium path. It is not the subgame equilibrium, it's the path that we end up. Sometimes in problems I ask you to define the path. Sometimes I ask you to just identify the subgame equilibrium, and sometimes I ask you to do both. Okay? So you need to be careful to distinguish between them. Subgame equilibrium path is the path the game ends up. Here, the subgame equilibrium path is described as follows. You can either simply write YZ, or the correct way is to say player 1 plays Y and its first information set, and then player 2 plays Z at its second information set. And the game will end up with 2 and 1 for player 1 and for player 2. Okay? Any question? Good. So this is the slide that basically writes whatever I just said. Now, a more complicated example. Here, this is a combination of sequential and simultaneous game. So the game has 2 parts. First, player 1 moves, then player 2 decides to play A or B. If player 2 plays A, then she has C or D. If she plays B, she has E or F. And this E or F will be placed simultaneously by the player 1 again by actions G, H, and I. Okay? So this example was very confusing to me when I was a graduate student, because I wouldn't know what to do when I wanted to find the subgame perfect, and I made lots of mistakes. But if you look at the slides that we had previously, there are a couple of points that you need to make sure. First thing that is very important here is that player 1, when there is a dashed line between the decision nodes, these are essentially means the same thing. So in any strategy profile, it is not possible that player 1 plays something to the left and something else to the right. Okay? So you cannot say in a strategy profile, player 1 plays I here and H there. That's wrong. You will simply say I, because then she plays I at both cases, because this is simultaneous. Player 1 cannot distinguish between left-hand side and the right-hand side in this particular part of the game. So therefore, whenever you have best responses, note that it has to be like this. This is for example. This may not be a best response of this game. What I'm trying to say is that this cannot be a best response when you find the subgame, because these 2 decision nodes are the same. The mistake that I made in the midterm exam, because this was a midterm exam at that time, was putting I in one of the information sets and H into the other. The reason that I'm telling you this is to tell you that I'm not from the moon. I'm the same person as you, and I made these mistakes. So if you make a mistake, don't worry about it. At this stage, it's perfectly fine, but try to be very careful and don't do them in the exam. Otherwise, you lose mark. That's why I lost mark. So I, H, or GG. When there's a dash line, it cannot be something to the right and something to the left. Another point, when there's a dash line, this cannot start a sub-game. So therefore, this is not a sub-game. Okay? So if you consider these two, with a high chance, you won't make the mistake that I did, and you will get the full mark. Now let's see how we tackle this problem. The first stage is to find the sub-games. Now, how many sub-games this game has? Three. Any other numbers? Okay, yes, 3 is the correct number. Thank you. Yes, 3, because so we have 3 decision nodes, 4 decision nodes, 1, 2, 3, 4. This one does not satisfy a subgame, as I just said, because it has multiple decision nodes in it. Therefore, there are 3 subgames in this game, and those 3 are this, and the whole game. Okay? Now, the next step is to find the SPE. We use the backward induction, and we use the best response argument. I'll start with 2.1. At 2.1, it's this the player's 2's turn to decide, and the best response of player 2 is what? C, because 2 is larger than 0. So I'll put an arrow there. Now let's go to 2.2. 2.2 is the time for player 2 to move. If player 2 moves E, then what would be the best response of player 1? If player 2 moves F, what would be the best response of player 1? I mean, that's another mistake I made. I tried to solve this game with my mind, which I couldn't. This is very difficult, because what I did was say, okay, if he makes E, then let's compare these, player 1. So this is better. Now if he plays this, then this is better. And that was my answer, which is wrong. It cannot be the case, GI, because these are the same decision nodes. Now, how can we do that? Of course, there are ways you can do it on the tree form, but I highly recommend not to do it at this stage. Maybe when you get more comfortable with games, you will be able to do it. But at this stage, I highly suggest to transform this subgame to normal form, find the NE with the method that I just told you, star delta, and then substitute the arrows to the game. Okay? That's the easiest and safest way. There will be ways that you will be able to find the NE via the tree format without transferring to normal forms. I think your tutors will let you know, and if you wanted to know it, I'll be more than happy to do it for you. But the safest way is just to transfer this game to the normal form. You know how to transfer this game to a normal form. I mean, player 2 has E and F, player 1 has G, H, I. Now you know how to find the Nash equilibrium of this game. If player 1 plays, so let's do it the opposite way. If player 2 plays E, the best response of player 1 is to play G. Now, if player 1, I'll switch it, because I didn't do it at the beginning. What I did do at the beginning of showing you how to find the Nash equilibrium was to find all the possible best responses and take the box which is the mutually best response. But another faster way of finding the Nash equilibrium is whenever you get a star, immediately switch to the other player and see that the star would give you a delta or not. Okay? Now I got a star here. Now what if player 1 plays G, then 6 is larger than 0, so this is a Nash equilibrium, okay? Now the question is whether this is the only Nash equilibrium or not. I guess for this example it is not. There must be others. Let's see if this one would characterize an NE. if player 1 plays I, then the best response of player 2 is to play this. Let's do all of them. So if player 2 plays E, the best response was that. If player 2 plays F, the best response is this. Now if player 1 plays G, we got it. If player 1 plays H, and if player 1 plays I, so we have only one Nash equilibrium. I think it was in your, I don't want to spoil next week's assignment, but there might be some assignments that give you multiple Nash equilibria. I'll let you know how to handle that. But here for the moment, we have one Nash equilibrium, and that is GE. What should I do? I need to substitute it into the table, into the tree. That is, draw G and E here, and eliminate all other parts of the game, which are these parts. Okay? So now, from now on, if I get to this sub-game, I know I'll end up here. Okay? But if you wanted to do it the way that I did initially, by trying to find it via the tree, it would be more confusing. Now, this is the way that you know, whenever you get to subgame 2.2, you will end up at 4 and 6. Okay? Now, the last subgame that I need to work on is 1.1, or the whole game. It's player 1's turn to move. Player 1 knows if she moves A, she'll get this. And if she moves B, she'll get here. 5 is larger than 4, so this will be an arrow. Now the SPE of this game is, this is the difficult part. How many elements do I need to have for the first player? Do I need to have 3? No, because this is one decision node. So there has to be equal to number of decision nodes. So player 1 has A and G, and player 2 has C and E. Okay, so the SPE of this game is AG and CE, the only SPE. Now if we found multiple Nash equilibria here, as I said in the definition, you need to do the process twice, okay? Once do it with the first Nash equilibrium, which is this one. Suppose this one was also a Nash equilibrium, then once I do it with this one, I find the first SPE, then I'll do it with the other one, which is 5 and 3, to remove these arrows, draw the new arrows, and go to the other subgame. That could change the decision of player 1, I guess, I'm not sure, but of course for this game we have only one Nash equilibrium, therefore we had to do it once. But in any subgame, if you had multiple Nash equilibria, either use 2 different colors, or you may be able to use stars rather than arrows, and therefore you need to repeat all the process again to make sure there will be obviously more than one SPE. This example is not one of those, but we'll give you some of those examples as well. So we have like 5 minutes. What I'm going to do, I'm going to discuss the last example we have today. 2 players start with $1 in front of them. Player says stop. Each player gets what's in front of them. If a player says continue, $1 is taken away from him, and $2 are added to his opponent pile. Okay, the game will go for 4 rounds, and obviously it will finish after that. The reason that I did it horizontally is that sometimes if games have more than 2 steps, then it would be very difficult to draw them vertically. They'll go out of the box. And not only that, but also some textbooks use these notations. So here, what I could do, obviously I would keep my original notation saying 1.1, then 2.1, 2.2, then 1.2, 1.3, blah, blah, blah. And when I say 1 here, this does not mean that this decision node is 1. This means that this is player's one turn to move, okay? So don't get confused between 1.1 and 1 here. So this is a different way of representing games. Sometimes textbooks use this method. So they don't try to name the decision nodes and information sets. The reason that we did it, obviously, in our lectures was to make things more important, more, let's say, informative, and therefore be able to find the subgames. But at this stage, even somebody doesn't do that, you should be able to find the subgames. Now, how can we do that? We'll start with the end of the game. Of course, before we start any analysis, again, this is one of the games that we say, yeah, it should end up somewhere here. So this is one of the SPEs that is also not reasonable. Not reasonable meaning that both players do something which is worth for both of them. So we will say, yeah, why should you say continue? Let's wait. Sorry, why should you say stop? Let's wait until we get to the last. And we get both $4. But as you can see, the SPE of this game is not that for 4. Let's see why. First, we need to find the number of subgames of this game. How many subgames this game has? Any guess? Remember, this is a sequential game. After every move, the other player moves. So we start a new game and new sequence every time. So there are many subgames. I don't even know unless I draw them. So it will be 1, 2, 3, 4, 5, and the whole game. Okay? So the reason that I'm doing this is to show you that if the number of subgames increases, this is not necessarily a bad news. Now, let's start with the last subgame. It is player 2's turn to move. What would be the best response of player 2? Is to choose S, because 5 is larger than 4. Now, one step back, it's player 1's turn to move. Player 1 knows if she continues, she'll end up with 2. But if she stops, she'll end up with 3. Therefore, this is the best response of player 1. Now it's player 2's turn. Player 2 knows if she continues, she'll end up with 3. But if she stops, she'll end up with 4. So this is the best response of player 2. Now player 1 knows if she continues, she'll end up with 1. Here is 2 is larger. Again, this is the arrow. Again, player 2 knows she'll end up with 2. 3 is larger. Arrow. Player 1 knows end up with 0. 1 is larger. Arrow. Therefore, the subgame. So now, can anybody tell me what is the subgame perfect equilibrium of this game? Exactly, too many S's. S, 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 S. 3 S for each information set of a player. And what is the subgame equilibrium path? Along the subgame equilibrium path, player 1 decides to stop at the beginning, and each player gets $1. Okay? That's very easy. So the path is just end up here. Nothing else is relevant. So again, as you can see here, the equilibrium is not as reasonable as we thought. This is again because there is a cheating element in this game, and that cheating element is where player 2 cheats and gets 5 rather than 4, and vice versa, again up to the first subgame, which is the whole game. And nobody gets nothing. Okay, we are done for today. Best of luck. Before I finish, so please, before sending an email, listen to lecture notes, look at the course profile, look at the materials on the blackboard, and then send an email. We have like 140 students in this class. I've got lots of emails that the answer is obviously there, but people didn't mind to just look at the profile. So just look into the materials before you jump up and sending an email. I know it's the least cost for you, but it's too costly for us to answer 50 emails every day, okay? Thank you. Yes.
So I just want to confirm that parents have lots of hours of is that right? If you go to parents, I mean, and I think if you go to you try to ask about his class, or I mean, they're both game theory.
No, this is office hours. He's out a tutor as well. He's one of my tutors.
Okay. Okay, I got it.
Sorry, it's a bit confusing.
Yeah.
Oh, I think I forgot to add his name in the Blackboard because I mean one of the tutors decided to reduce his hours.
Right.
So we had to add parents to our team.
Okay.
Yeah.
Okay, so, but he's teaching 70.
Yeah. He's teaching another course as well.
Okay.
Those are separate things. He's tutor as well as teacher.
Okay.
Jordan, so for the first assignment, we don't need to submit, right?
No.
So there's no link.
No, but from next week there will be a link, and the deadline is Wednesday before the class. No worries. No worries.
Yeah, in general, I think probably started like 17. On there, you usually the predictor assign a probability to each player for their actions. So for this question, if we just assign when he assign probability for each player's action.
Let me stop you here. It depends what kind of equilibrium you're looking for. Here you're looking for pure strategies of the imperfect equilibrium. So pure strategies of the imperfect equilibrium does not require you to assign any probability. If I ask you to find mixed strategies, then you were obviously right. So, but here, since we are in, so the only part which was mixed strategy was the natural equilibrium that I talked to you the other day. The other slides. But this one is pure strategy, so you don't need to assign it. You will get to it.
Yeah, because I know that if you assign probability for each player's action, you really can determine which is better response to the exact payoff for that, right?
That's what you get. The mixed strategy.
Okay.
That's exactly the couple of previous slides that we had.
All right.
This is pure strategy.
So don't need to.
No.
Thanks.
Yep.